Okay, thanks everybody for coming. And RExc seminar continues today. And thanks to Nikolaj Tatti, who's an assistant professor here at the University of Helsinki, and is going to present this work about Coresets. This is actually a super interesting topic, so I'm very interested and curious about what you're going to present today. And yeah, I'll leave you to talk. Thanks.
Okay, so this is a paper that I did with Nikolaj and RExc. So this was accepted this year, and actually I gave this talk already at the conference last week. But this is a little bit more extended talk. So let's go over it. So let me first talk about like what's the problem setting here and what we're trying to solve, because the problem we're trying to deal with is a little bit more involved than usual. So let me just start with a kind of like motivating example of what's happening here and what we're trying to achieve. Okay, so let's start with just a simple example. So let's say you want to do like a recommendation of K movies. So just to recommend top K movies. So this ranking is not like personalized. Like it can be derived from some data, but it's not like some user comes in and saying like, oh, like I like these movies, give me some new movies, but it's just a global ranking of like top K movies, and then you show it to a user, like someone who wants to see it, and now that user said like, oh, I have seen half of these movies. So can you give me, can you get rid of these movies and then then give me a new list out of it, also top K movies. So what can you do in this case, right? And then in this case, you can either remove the movies that you know that the user doesn't care about too much, and then just rerun the whole thing from the start. That might be expensive, like if you have a very large database, you have lots of users, like this costs resources. Or another approach, and this is what we are actually looking at, is that you select some small set from your database, just which essentially some set of movies. This set of movies will be much larger than K, but also much smaller than the original database. And then from that list, you actually make your selection. So like once some stuff gets deleted, once you say, okay, I don't care these movies. So the idea there that you do a bit heavier pre-computation for stuff, you get some summary, which is called Coreset. And then after that, the user comes in and says, like, oh, I don't care about these things, these items, these movies. Then I have a second algorithm that lists stuff, and then this will be faster because the set is just small. So that's kind of like the set of what we're trying to do. So a little bit more like in abstract form, just the same thing said, but in a little bit more formal ways to say it. So we have a function f. So this is something that we're trying to optimize. So this tells it how good is our list is. It takes a subset of, it just takes a set of items or subset of so these are universe. It just takes that as an input, and then it outputs a real number saying how good is our list. Larger numbers means that it's better. We also have some constraints on what type of solution needs to be. We said it needs to be K movies. So that's one type of constraints we consider. We also look at the other constraints as well. But I'll talk about the function f and then also about the constraints a little bit later. So we want to do two algorithms, algorithm 1 and algorithm 2 on the designer. Such that algorithm 1 will construct this coreset, this summary of the whole universe, and then algorithm 2, which is giving this coreset, will give us the solution such that the solution in this test should be will be a subset of coreset minus d. D is the sets that user wants to delete. Okay, so D is actually an argument to algorithm 2, so I didn't put it there. And then the solution that we get from algorithm 2 is somehow very close to the optimum solution. That is that the solution that we will get if we just find the optimal solution by looking the original data minus the stuff that we did, like in the ideal case. So how close can we get to that? And then ideally we want C to be also somehow small, such that the whole setup actually makes sense. Some small detail here, which I don't really mention, is that actually this coreset, this C is actually not one set; it's actually multiple sets. It can be multiple sets, but then we just look at the size of it. And then we just look at the union of all these sets of items. All right. So okay, so let me say a few things about this function f. So because it's not some just generic function f. So let me just go over it. What kind of function we want to look at. So first of all, we require it's positive. So all the numbers are going to be like we don't allow negative numbers. Already, it's just because that's how it's typically done. This is such a huge restriction. The next thing is that it needs to be monotonically increasing, meaning that if you have some set of things and then you add some more items to that set, the function can only go up. Right? So if you have A and B, A is a subset for B, then FA is smaller or equal than FB. Right? So that's more increasing. And the last thing is, and this is the most involved one, is that it needs to be submodular function. And what is submodular? Whenever we add an item, in this case x, to a set, the gain that we get, and the gain is positive because the function is always increasing, that the gain is decreasing. So it's called diminishing returns. So fx, if we add x to a, the increase of function there is larger than if we add x to b, if b is a superset of a. So like whenever you add x to a larger set, there is the gain that you get there is smaller than if you add x to a smaller distance. That's the definition of submodularity. You can think it in a way that it's kind of like a combinatorial version of a convex function or a concave function. Depends which one you're going to. Anyway, so that's the definition of submodularity. So we're looking at this type of function. All right. A few words about the actual constraints. We do need a constraint because if we didn't have any constraint, then the optimal solution would be just a coset because the function is monotonic. So we can just dump everything like in dump the whole universe minus the deleted set in our solution, and that would be the solution. So we need some constraints on that. A very typical constraint would be a cardinality constraint. So say that, okay, you can only have k items in your solution. There are some more general constraints, which we will also look at. So-called matroid constraints. And these are like certain families of subsets of B, essentially. And these families have some properties, which I'm not going to give you the exact definition for it, because it doesn't serve purpose for its presentation, but it's certain sets of certain families of subsets of B are called matroids, and specifically they are downward closed, meaning that if there's a if you have a matroid M and then a set belongs to that matroid, then all the subsets are also belonging to that matroid, so that's called downward closed. And then the second property, this is not the definition, but this is like how you can think about it, is that all the maximal sets have the same amount of items. That's not the definition of matroid. It's a little bit more strict, but that's like the main property that kind of defines it a little bit, or like one of the main characteristics of matroids. And then we can handle p simultaneous matroids. So we may have like p different matroid constraints, and then we say, okay, so we're giving these constraints and saying, okay, so find me a set that maximizes f. That also satisfies these p simultaneous matroids. Right? So that is the constraints, right? A few words about the actual adversary. So that's the third thing. So what items can we delete? So we need to make certain restrictions on what can we do there. So adversary can delete any set D from the possible items. Now we don't know this set D when we construct our coreset, but we do know the size of it, or we know the upper bound for it. Like let's call it small d. So how much teacher can delete? Because our algorithms will depend on this d. Because the more items you can delete, the harder the problem is. The larger the coreset needs to be. Essentially, that comes up down to that. So we need to know in advance how many items user can delete. Obviously, this is just for the theoretical guarantees. Like the algorithms will run in practice, we just don't get any guarantees. Like if the adversary gets more than what we initially thought it would delete. So the deletions are arbitrary, but they're static, meaning that so the adversary knows our methods. And it knows the data, so it can kind of simulate what we are doing, and it can make choices. But what it doesn't know is that if we make any random choices in our algorithm, then the adversary doesn't know what random bits we used. So it doesn't know what we end up doing in the end, but it knows the method, and then it can do what it can do its worst based on the method and based on the data. But it doesn't know exactly what we're going to do. And we're going to abuse this fact because we will have some random components in our algorithm. And this actually will allow us to actually make things work the way it works. All right? So that's about the adversary. Okay, so a few things about the actual computational complexity here. So let's just forget about just the coresets and then the whole deletion thing. We're just looking at the maximizing the function, submodular function, given some constraints, right? So just that single component. Now we know that this is a very classic NP-hard problem, and we also know that there are approximation algorithms for this problem, and these are very classic results. Essentially, there are algorithms for which we can find solutions. So they are polynomial algorithms, and they are very simple, typically very like a greedy construction. You just find a set. You just find the best item that you add in the set, and then you find the next best item, and so on, and you keep adding stuff greedily until you hit the constraint. That's typical greedy algorithm. We're not going to use those steps. We are going to use a slightly different algorithm for our purposes, which I'm going to talk about later. But typically with these algorithms, you can show that that there's alpha is constant, such that the solution that this algorithm finds you is and its cos fs is its quality fs is larger or equal than alpha times the optimal, where alpha is something smaller than 1. And then the actual value of alpha depends on the type of constraint you're using. If you have a cardinality constraint, it's 1 minus 1 divided by e. With other constraints, with matrix constraints, you get slightly smaller alpha. So, okay, if the coreset is the complete data, if we just return the whole data, then but that's not what we're trying to do. We're trying to find some small set, and there's going to be some trade-off between how much small set can we have, and then how good approximation ratio can we get by just selecting that. But the point being here as well is that even if we return the whole data, we cannot solve the problem exactly like in reasonable amount of time, but we can get some approximation ratio. But the approximation ratio we get with coresets are slightly worse than what we get in ideal situation. And then there's some trade-off between the size of the coresets and also the approximation ratio. Well, we can get from that course. All right. So okay, so we're not the first ones to actually think about this problem. So there are other papers. So we proposed like I think 5 different algorithms in this paper. I'm not going to talk about all these algorithms. I'm just going to talk about 2 of them and not going to go through all these proofs here too much. But just to show what's happening there, that like in certain cases we can get a depending on what kind of adversary, what kind of constraint, and is the algorithm that we're running, is it streaming, meaning that we just go over item once, or if it's offline where we can just do multiple loops over the items. That's another aspect. So we get slightly different guarantees, and we tend to beat them well, at least on theoretical level, we beat baselines. For example, like here we have the same guarantee. So 1 minus epsilon divided by 2. Epsilon is a user parameter that controls the trade-off between the guarantee and the coreset size. And then like the baseline gives you epsilon square, and then we get epsilon here. So like these small improvements, but improvements nonetheless, at least on theoretical side. All right. So let me talk about. So I'm going to talk about 2 algorithms here. I'm going to talk about so this algorithm first. So this static with p-matroid algorithm, and then I'm going to talk about well, this one, the last one. So this is p-matroid. You can think about p-matroids and look like. So I'm going to talk about how they look like. So let's start with the streaming algorithm. So this is actually, so we start with an algorithm that wasn't that is not ours, but this is just our starting point. And then this is a very straightforward algorithm. The idea here is that, okay, so you have your items, you just go over them in a for loop. Then you have set I. I is your current solution. You start with an empty set. And for each item, you first compute the gain of adding b to the current solution. You call it the weight of the particular item. Then you have this function exchange. And what it does is that it finds the set, like if adding b to I violates some constraints, it finds the set that should be deleted from your solution such that the constraints are satisfied again. For example, if you have a cardinality constraint, it just picks one item out of your tentative solution, and then this item should be this item should have the smallest weight essentially. So it's just to find like the best item that can be the best item that can be removed, or like the one that has the smallest weight essentially. With p-matroid, it's a bit more complicated. This is a bit more complicated, but it just finds the purpose of that function is just to find some items that can be removed such that adding b doesn't violate any constraints. Okay. And now, if the weight of the new item is larger or equal than 1 plus gamma, gamma is just a user parameter. You can think we just set gamma to 1 all the time, so 2 times the total weight of the exchange set. So this W weight of W is just essentially the sum of the items in the set. So if the weight of the new item is larger than equal than 2 times the weight of the item that should be removed, then we swap them out. We remove the W and then we add E to the set. Okay, and we just run this algorithm over all items. Now again, very simple algorithm, and then you can show that if we set gamma equal to 1, then the approximation algorithm is there's a guarantee that this algorithm will give you 1 divided by b approximation guarantee. And this has nothing to do with coresets or deletion whatsoever. This is just to optimize function f over the constraints. Right? So you get this approximation guarantee with this particular algorithm.
Can you repeat what P was?
P was, sorry, yeah, P was the number of constraints you can have with this well, common matrix. All right. So like if you have a cardinality constraint, then this would give you 1 divided by 4 because it's just one constraint. which is worse than the best approximation algorithm, but this is streaming algorithm and the other one isn't. And we are going to use this algorithm in certain ways. All right, so we are going to use this algorithm and do something else with it. And so first, let's construct a coreset. And so this is the first algorithm. So this is the actual alg1, which constructs the coreset. And then the next slide is going to be the actual set that constructs the solution. So the algorithm is also, so it's a streaming algorithm. You just go over the items. It returns you two sets, I and C. So I is kind of like the tentative solution, and C is your coreset. Although technically both I and C is your whole coreset. So C is like the items that you kind of are reserved, that you need to add later in algorithm one, and then in the next algorithm, and then I is your like kind of tentative solution that that this constructs. But both sets are needed, and they're part of the coreset. So you go over the, so you start, so both are empty at the beginning, and now you go over the items again in the for loop, and you keep adding this, you keep adding items to your coreset, to C, and then the moment this coreset gets too large, and so D divided by epsilon, you're going to sample an item and remove it from the C. And then with probability that is 1 divided by the gain of having that item in adding it to a current tentative solution. This means that items that have low gain, so the bad items, will get removed first from C, and then once we get that item, we will try to add that item to our tentative solution I. And we may succeed adding it, or we may fail adding it, but we try adding it and then see if we can add the item. And that's the algorithm essentially. So essentially we are using this this exchange algorithm, and then we have some additional structure on top of that, and then we are feeding this algorithm, this previous algorithm, this X, we are feeding it items that we are sampled from the course. So that's the algorithm. All right. So that gives us a coreset. So what's then the actual solution? Again, very simple. So now you have your I and C. This is your coreset coming from algorithm one. Now you have your set D. These are the items that user doesn't care about, which we delete. Now what we're going to do is that we're simply just going to run over C minus D, so over our reserved list, and try adding those items into our tentative solution, right? And then again, using this X algorithm that like we talked about a few slides before. And once we're done with that, we're just simply return I. And then, because it still might have some items from them that should be deleted, and then we just return I minus D set. So that's our algorithm for finding the solution, at least. So two very simple algorithms. So what can we say about them? So first of all, just the size. So this coreset size. So the I, this tentative solution, has at most k items. So k can be, if you remember what k was, it was if you have cardinality constraint. So k is just how many moves you have. If you have matroid constraint, then k is just computed from how many those matroids. As I said before, like it has maximal size. All the maximal sets will have all the maximal. All the maximal items in matrix will have some same size. So that's just that essentially. So it's just that number. And then C, just by the definition of how this algorithm works here, just by definition will have at most D divided by epsilon items. So that's the coreset size. So what about the approximation ratio? So if you just look at the algorithm, what happens here? So algorithm 1, so feeds B minus C items to this X algorithm. And algorithm 2 feeds C minus D items to X, right? And just look at, if you just look what's happening, let's go back. So here, the items that are fed to X are just D minus C, because well, that's just how it works. And here it's just C minus D, right? So you can think that I, so this, sorry. So I right here before the return, so I here. Sorry. That's just the output of running this X algorithm with the input items of B minus C and then union of C minus D. So this is what we will be doing. Now, let's just write O1 to be the optimal set in B minus C union C minus D. So what we're feeding into it, I mean, subject to the constraints. And then let O2 be the optimal set of B minus D. So this is actually what we want to find. And now, because if you look at these two sets, so this set is larger than this set, which means that O1, FO1 is better than FO2. Okay. Now, okay, so we get that FO1 is better than FO2. And in addition, so we can see that Fi is larger than FO1 divided by 4p, which was the first approximation ratio we got from the, well, this approximation ratio followed by, from this first streaming algorithm. And because, well, because of this, we get FO2 is smaller than FO1, so we get this inequality as well. Okay. But this is not what we actually return, because we don't return Fi, we return Fi minus D. But we can show that Fi minus D is actually 1 minus 2 epsilon times Fi. And I'm going to spare you the details how this is shown, but it relies on all the small details that we show in the algorithm. That there's a reason why we take D divided by epsilon items, and the reason how we sample small things. But if you modify these things, you will get something else. So there's a very it's kind of like doing greedy in a batch sense. So you start with your so you have again your tentative solution against I, and C is also you kind of reserved items. So you start first by selecting top D items in V according to just the weight according to FB. So whatever the items are better, you just select top the item and then put them in a reserve. Once you've done that, then you start doing this loop where you select D divided by J epsilon items, where J is just a counter, and then D and epsilon are the parameters that you select those top items according to according to the following gain. So you select those top items, and then you add those new items into your research set, and then you sample an item from that batch, again with the same probability of 1 divided by f di, and then you add that item to it, to your solution, and then you remove all the items from B that are that can be added without violating the constraints. So essentially, you get rid of the items that can no longer be added I, otherwise you would violate the constraints. And you keep doing that until you run out of items. All right. So that's the Coreset algorithm. The offline algorithm is even simpler than the previous one. Essentially, you run a greedy algorithm for your reserve set. So this is C divided by D. And then you just return whichever is the better solution of the two, either I minus D, so your solution that you construct from the first algorithm minus the deleted set, or this new greedy solution that we should compute from C minus the stuff that we did. So that it's a very simple algorithm, but analyzing it is a little bit tricky. So what can we say about the Coreset size here? So just talk about this reserve set. Well, if you look at it, we added D of items there, and then upon every step, we add D divided by J epsilon amount of new items to this Coreset, and then this for loop runs at most k times, because otherwise then you cannot longer add any stuff to I anymore. So you get something that looks D plus sum over J plus 1, J going from 1 to K, and then Rj is just the batch that we add at J iteration. So you get something that looks like this, which you can show that using some kind of inequality that this is at most log K. And that's why you get something that looks like the Coreset that will be K plus D divided epsilon log K. So that will be your Coreset size. Then the approximation ratio is something that looks very complex. But maybe the main point with this approximation ratio is that if P gets large, so if we increase the number of matroids, the approximation ratio will go down, so the problem becomes more difficult to solve, or you have worse guarantees. And also, if epsilon becomes large, then the guarantee will also go down. All right, so that's the offline algorithm. So let me just show you some experiments that we did. So we had some bunch of data sets, not all of them are shown here. So we took these data sets, we selected some very specific optimization functions, how we should optimize also, and the criteria. So the algorithm that we run was the blue, and then the orange are algorithm. So this RExc is the streaming version. X2 is kind of like the variant of the streaming version, where we just run two parallel algorithms and then just combine the solutions. Then our greedy is with the ones that I just talked about, and then the red and purple are the baseline that we used to compare. So the x-axis is the Coreset size, and then the y-axis is the performance. So it's F essentially normalized. Although you don't see the scale, so the normalization doesn't matter here. So we are doing quite good. So the greedy algorithm does the best, pretty much always the time. And then the streaming version, the red one, is also doing well, not red. The orange one is doing also quite well, and then also the red one is also doing. The base, its performance is kind of like they're very close to each other, the orange and then the red one. So our algorithm and then the baseline. But there's a good reason for why the red is. There's a drawback in using the baseline one is that it requires some it's computationally more heavy. And then you can see there, so the running time starts to grow if we start to increase the parameter D, which is how many items can we delete. So the running time for that algorithm starts to increase while we are relatively stable. So that's our benefit compared to the baseline. All right. So just to conclude, so the idea here is that just find some small set of original data, which we call coreset, so that you can re-optimize after some deletions. So the function that we were looking at here to optimize was submodular functions, and then we have some constraints. Offline algorithm works well. Streaming is also fine. If you need streaming, you can use the streaming one. If you can get away with greedy algorithm, use that. So that's about it. I would say, like, to me, this paper is more like a study of what you can do with corsets, and this setting is very specific. It may not be the one that you're interested in, but then the general idea of doing this re-optimization on a small set is kind of interesting. So maybe there are some other problems, different optimization problems that you can think of, where this kind of approach makes sense. So that would be kind of interesting, like a line of work to look at if someone wants to think, but where to go next. All right, thank you.
Thank you. Thanks. Really interesting. Are there any questions from here? Otherwise, actually, so that's all. You had some test experiments that you were using. So can you make other examples of applications that where these could be useful? You made it like the movie example.
Yeah. It's a well. I mean, okay. So it depends a little bit. So here, like with these submodular functions, okay. So typical submodular functions are, when you're working them, that typical submodular function is some kind of cover function. Meaning that you are a very prototypical submodular function is like you're giving us a family of sets, and you want to find like k-sets that maximize its union. So that's a very prototypical submodular function. Now this type of functions occur, for example, in social network analysis. Not sure exactly how would you use that, but certainly those functions appear there, where, for example, like you're trying to, for example, select k nodes that would have at most neighbors, well, combined together, and then even to extend that, you would use like some kind of like influence maximization problem where like let's say you want to spread influence, whether it's advertisement or a virus. So you try to pick like k nodes which would spread as much as possible here. So that's a typical submodular problem. Here, and then maybe you can come up with some scenario where the leading stuff works here, like maybe an ad agency, like working saying, okay, so maybe these people that you want to influence, and then the ad agency is like, oh, we worked with these people before, we don't care, give us a new set, maybe something like that. Sure. But again, this is a very, very specific scenario where you can only, this is a very specific problem. I would say the idea of doing the summaries, to me, it's more interesting than just this particular optimization problem, I would say.
Yeah, the coreset idea.
Yeah, the coreset idea. So it's essentially that you do re-optimization, not over the whole set, but on some smaller sets.